So hello everyone, I will present you my paper, or the presentation about my paper, whose name is Smart Anomaly Detection and Monitoring of Industry 4.0 by Drones. I'm working in the lab stick in France, and I'm part of the University of Britain Sud. So first of all, the introduction. So today there is a new context of industrialization and digitalization of production. Brings the notions of automated responses, Internet of Things for industries, IIoT, and concept of Industry 4.0. What is Industry 4.0? So the concept of Industry 4.0 brings the drones and most of that, the flying drones. These drones will be more and more used for example, area surveillance, monitoring missions. They can be generally used outdoors or indoors, but there is more constraints as there are more obstacles like walls or no GPS signal. The objective of our project is to set up an architecture which allows communication between the Industrial Control System, ICS, and flying drones, unmanned aircraft vehicle, that monitors the environment. The UAV should know where a problem occurs and how to move to the area affected. It needs to function indoors and outdoors and take one or more images of the problem and detect an anomaly using an embedded neural network algorithm to confirm or deny the anomaly. And then finally, thread the anomaly accordingly if one occurs. So in the first part, I will present the related works we found in the literature. Next, in the second part, I will present the methodology on how we worked on that. Then the results of the project, and I will do in the last part a brief conclusion. So the related works. So drones can have many uses in the industry, including monitoring of an area, supervision of industrial processes, etc. Most of these missions were usually performed by remotely controlled ground robots, and more recently by unmanned ground vehicle, UGV. UGV must advance on the ground, on defined paths, and avoid humans, machines, while moving quickly. But they can't address all current use cases in industry. UAV can be used to communicate with other drones, ground or aircraft, to meet specific needs like space surveillance or fall detection, to monitor, inspect, or collect data. They can mount multiple sensors on elements, like a camera that can take a picture of an event and send it to the cloud, a server, or even process it itself. Now the second part, the methodology. So here we have the general architecture of the project. So here we have the Schneider platform with a replica of a pharmaceutical industrial complex. This platform communicates with a SCADA server with the protocol Modbus TCP IP. On the server runs a Java application and a database. The Java application can access the database and save values in the database, but also communicates with the drone. The drone communicates with the database, the Java application, and also with the Raspberry Pi with the embedded computer for this project. To position the drone in the room, we use the decawave cards with the protocol of UWB communication for ultra-wideband. So we use some anchors in the room and one tag placed connected to the Raspberry Pi to locate precisely the drone. Now the part of anomaly management. So industrial processes may encounter some anomalies during their functioning, like production order is not executed with the right equipment, or production order is not executed with the correct material, or quantity requested is not capable of being manufactured because there isn't enough quantity in the ball in the platform to do that. Then, to confirm the cause of an anomaly, we need to get fine-grained data from the industrial process and compare data to the normal values to detect any height deviation during the manufacturing processes. If values differ too much, there is an anomaly. What we have? A drone. There is some constraint for this drone, this UAV. It needs to be positioned indoors, so we can't use the GPS because the room is made a lot with metal pieces and in the first floor of a third floor building. The precision we want to have it's a few centimeters, approximately 5, but the inertial measurement unit isn't precise enough to give that. So the solution, I speak about that in slide before, but we use the ultra-wideband with decay wave cards. Now, to continue with the drone, what is the required equipment on the SDK to add to this drone. So we need to have an UWB tag to position the drone inside the room, a camera to take pictures of the platform in order to detect any anomalies, and an embedded computer, Raspberry Pi 3B Plus, to manage all the elements, drive the SDK, and connect with the drone through UART to access sensors value like speed, acceleration, heading, altitude, etc. Now the second part, indoor positioning. So we have the DK-Wave MDEC 1001 cards, UWB communication protocol. They have two functions. They can be anchors or tags. Anchors are located in a known position and periodically transmit signals. The tags listen to these signals and determine a distance between them and the anchors. The tag is positioned on the drone and connected to an USB port on the Raspberry Pi, and anchors are placed in the room. The last part for that is indoor displacement. We choose to set the drone to fly at a constant altitude to avoid collisions with humans or with machines. Go straight to the destination from point A to point B, but to do that, it has to rotate from its initial orientation to the orientation required to reach the destination. To calculate that, we do linear interpolation from the initial orientation. Like we can imagine if the drone is oriented to north and we want to go to south, we do we can see here there is a difference of 0.9999. So the drone will do with linear extrapolation, we convert this 0.9999 to degrees from 0 to 180. The value here are negative because we are going from north to south by passing by west, and they are positive when we pass by the east. And on long distances, it is possible to adjust the heading of the drone to be more precise to the location at the end. Now, the anomaly confirmation and diagnosis. The UAV should analyze images itself to confirm or an anomaly and make a prognosis with a convolutional neural network, CNN. The UAV sends the image to an operator if an anomaly is detected. The CNN needs to be executed in the Raspberry Pi in real time, and the convolutional network we use is YOLOv5. So here the Raspberry Pi in real time, it's 10 Hertz, so 10 times in a second for one iteration. So to continue with YOLO-v5, this is a real-time object detection system. Once a model is trained, it can detect objects in a video in real time. So here we compare the different model given by YOLO-v5. There is an S, an M, an L, and an X model. We can see here the S is the fastest, but it gives some bad values of accuracy to detect from the dataset the values, the label. But here the X model is way more better to give some better results, but is a lot slower, like approximately 10 times. So to choose between the L and the M, we choose the L because it has a good compromise for speed. Here it's not really slower than the M, but it gives way more better results. So we choose the YOLO-v5 L model, and these values are given with the dataset COCO Val 2017, and the dataset is calculated with 5,000 pictures, with a lot like 80 label difference. Now the third part, the results. So to position indoors the drone, we compare two methods, the Bancroft method and the Newton-Raphson method. The test has been done with 7 encores and 1 tag. Newton-Raphson will take only the 4 best signals of the 7 encores. Like here, we have the drone, we have the 7 encores here. We can imagine that the Newton-Raphson method will take these encores, the 0, the 6, the 4, and the 5, because they are the closest, and we can imagine that the signals are the best with these 4. But if this encores as a worse signal than this one, this one, the tag, will take this encores and the third here. So to compare the method, I did 1000 iterations, and this is the value we add. So the execution time is the same approximately, and here we can see from the root mean square error, it's way more better from the Newton-Raphson method than Bancroft. So at approximately 5 times better. We can see here from the reality to Newton-Raphson, the difference are really small, like just here approximately 5 centimeters, with what is in our volunteer. Then the last part is the anomaly detection. So the anomaly we want to show is the lack of a tube on the palette and the lack of a cap. The palette is the little thing here. The cap is that, the little plastic round here, and the tube is like here, but this thing is a colored tube. The dataset has been done with 75 images, 25 of caps, 25 transparent tube, and 25 colored tube, like that. Labeling has been done with Label Image, which is an open source software available on GitHub. The anomaly detection has been done on a server with this configuration, and the dataset of 75 images has been separated in 50 images for training and 25 for testing. The training has been done with one batch, 100 epochs, and images of size 640 pixels, and that took about 3.5 hours to train the model. The results, so after the training, we try with the 25 images here to test, and all image taken has been correctly detected with the caps or the tube or the anomaly. Sadly, there is some false positive on the background for the tube. As we can see here on the confusion matrix, there is the cap who has been detected correctly, the tube here correctly detected as well, but here background FP, it's background false positive, and it shows that there is some false positive with the tube, and we can explain that by saying that if for the images that use transparent tube, the plexiglass around the platform will be probably see as a transparent tube for the algorithm in some shape of the platform. So this is why there is some false positive. So here an example of detection. So here the cap at 80% is sure, and here the tube at 90%. It's a tube. Here we have an example of a transparent tube. Now to conclude, so the architecture runs on a Raspberry Pi 3B Plus at 10 Hz easily. We have a lot more place, a lot more milliseconds to evolve. The UAV flies autonomously to the sensor where the anomaly has been detected. So from the point A where it starts to the sensor to point B and fly back to point A. The convolutional neural network, CNN, runs on the Raspberry Pi in real time, and the CNN YOLOv5 correctly detects all anomalies. So thank you for your attention. If you have any question now, don't feel free to ask.